We only use yours.
Okay.
Okay, hello everyone. We had to sort out our sound today. I hope you don't have a bad echo. We have a slightly different setup at the moment. Welcome everyone to the study season, second session with Mark Richardson, concentrated liquidity from scratch. In case you're watching via Twitter or YouTube, you can still register for the study season. Go to tokenengineering.net and register and have full access to all material and even have the chance to mint your NFT proof of knowledge. All right. I'd like to make you aware to a tiny giveaway at the Academy at the moment. We'll run the Token Engineering Track Day at EFCC on July 10th. Tickets are really hard to get. They are sold out super quickly. There's only one round of ticket sales left. And we are giving away 5 tickets for the EFCC conference for free. Just share this link to register at Token Engineering Reads, our newsletter. I'll share the link in a moment in the chat as well. And via these referrals, you have the chance to win a free EFCC ticket. All right. I think we are ready to go.
Okay. Can everyone hear me okay? Can I get some indication in the chat that you can hear my voice and it's clear enough that you understand what I'm saying? Perfect. Okay. I'm just going to share my screen. Okay. So yeah, welcome back. The second in our series of lectures on concentrated liquidity from scratch. And I wanted to begin by first discussing the homework assignment from last week. And maybe it's a good time to make clear that I do expect these to be completed. This isn't what I would call optional if you want the proof of knowledge recognition at the end of the course. So I didn't really set a deadline on these things, and I concede that I didn't necessarily make those course requirements clear in the first lecture, which is my mistake. And so for people that do still want to complete the proof of knowledge and mint their NFT at the end, you have basically until next week to complete the first homework assignment, and you'll now have the benefit of being able to see a few other people's being able to see some of the other submissions, which is, I think, a good way to collaborate in learning from each other's submissions anyway. And as you'll see at the end of the lecture, you'll need to do this anyway to complete this week's homework assignment. So if you haven't done it already, you'll have some catching up to do, and I highly recommend you get started on it. Otherwise, the accelerating rate at which we progress through the course material might start to seem overwhelming. But as I think I have demonstrated, I'm relatively open to people contacting me and setting up calls and things. It is important to me that everyone is feels comfortable going through the material, and I know that some of it is very challenging, but we can make things as easy as possible for you. I don't want you to feel like you're unsupported. So feel like if you need to reach out, if there's anything that's bothering you and you can't complete the work, just let me know, and I'm sure that we can talk through it and that you can get to the level of understanding that you require in order to feel comfortable with what we're discussing. Okay, so homework from last week. These are 4 of these are actually the swap equations that I presented in the last lecture, and 2 of them are derivable from the equations that I gave you, but I didn't actually present them. And so if you like, while you're revising, especially if you haven't completed the homework assignment yet, you may want to think about how these 2 equations in green can be derived from the other 4 equations in white. Now, one way that you might arrange these equations is via the inputs that they're expecting. So obviously, I think a natural way to read these equations is that the output is on the left of the equal sign, and the inputs are on the right of the equal sign. This is very similar to sort of the function notation. So for example, in the top row, you have delta x as a function of delta y, x0, y0, x and y, for example. And then in the bottom, you have delta y as a function of delta x and so forth. And we've shown algebraically, or at least I've demonstrated algebraically for the first four, that they are equivalent, right? There are various substitutions and manipulations that you can do to arrive at any one of those four from any of the other four. And in fact, this is true for all 6 of the equations that you see on the screen. But remember, I also told you that in theory, we are dealing with the real numbers, and this is where algebra lives. But in practice, and not just in blockchains, but anytime you're using a computer to perform a calculation, you're only dealing with rational numbers. And there are infinitely many more real numbers than there are rational numbers. Like there's a huge gap in the, between the theory and what you're actually able to calculate. And so one of the things that I'm going to do now is show you that while you're doing these exercises, there are ways that you can start to gain sort of a natural understanding for what the challenges are of actually implementing these things in a computer system, right? Specifically smart contracts in Ethereum, as is, the nature of the course. But also just when you're completing a homework assignment, right? I asked you to use any software package you like, be it Desmos, Excel, Python, Matplotlib, whatever you like, MATLAB, but all of these things are still computer systems. And so the answers that you generate from applying these functions still are going to depend on your choice of implementation. And in this case, the easiest way that you can sort of engage with that as a concept is to choose one of these equations or decide not to choose one of these equations and implement all 6 and see if you get different answers. So I've done that for you, and I'm going to share the code via the GitHub after this lecture. But what I've done is to sort of formalize this approach. So I've given these columns and rows essentially these variable names. So yn invariant meaning x0 and y0 and the y coordinate, x and y being the 2 coordinates wherever we are on the implicit curve at the time that we perform the swap, and then x and invariant being just the x coordinate and whatever the invariant is. And then all 6 of these equations I've implemented in a class called homework 1. And each one of these 6 equations generates, a result. Now, one of the things that you need to appreciate is that when you're using something like Python, which is where I've, implemented this, it, in a way, the implementation is kind of chosen for you. So, Python uses what's called a double precision floating point implementation. And this is using the IEEE 754 standard, which is something that you can look into. Maybe if you're a CS major or something like that, you might, find some of that stuff fascinating. In fact, you may already be extremely well versed on how that kind of thing works. But if you're just approaching these things for the first time, you should, and you're expecting to actually implement a smart contract, or that you're expecting to be able to be critical of other people's smart contract implementations, you should probably learn what IEEE 754 is and how it works and that sort of thing, because you may have to make those kinds of decisions, or you may have to reflect on other people's decisions with reference to at least the concepts in sort of how precision loss and accuracy are affected while maintaining a relatively wide range of possible inputs and outputs. So short version is there are 6 different equations to calculate a swap. I've implemented all 6 in Python, which allows me to do things in a relatively automated way. And so the class that I've created allows me to do a couple of different things. One of them is that I can feed in a series of different inputs, right? So you can see here in this list of tuples, the first string denotes whether or not this is a change to the X or the Y dimension. And then I have the value that I'm expecting there. So either X is increasing by 100 in the first instance, or dy is increasing by 321, and so on and so forth. And what this allows me to do is to essentially do back-to-back trades and see how these things end up, which also means that if there's like many trades, you can see how error accumulates in the system, right? You can perform maybe 100 million trades and then see just how far the rounding errors have taken you from where you're supposed to be. But it also means that we can start to ask the question that if we are expecting like 100 million trades to be performed, and maybe that's an extremely large number, but maybe it's not, how would that accumulation of error in the system be averted with a very clever smart contract implementation? Or what kind of security exploits does it expose that you need to be mindful of when you're implementing?
So we have a first question, I guess.
Go ahead.
Who raised his? Maya.
Yeah.
You raised your hand.
Quick question, out of interest, what does foo and bar stand to represent?
Maya, are you able to speak?
Can you hear me? Hello?
Can you?
Yeah.
I can't hear her.
Just go ahead, Maya.
Okay. If anything, I can type the question because I don't think Mark can hear me.
Okay.
Can you hear me now?
Okay. Maya, unfortunately, I can't hear you, but I will revisit this in a moment. Let's get to the end of the homework discussion, and then I'll close my presentation for a brief moment so that we can discuss things. Okay. So, for example, one of the things that I implemented is a log file. And what this means is that as the calculations are running, it will output the simulated trades for like all of these functions to a text file so that we can later audit that result. And so if there's a problem in the implementation, we can actually pinpoint exactly where it was. And you'll see here, I'm giving the output sufficient digits to capture all of the accuracy, or all of the precision, I should say, that Python allows for. And so you can see it's actually a very large number of decimal places here, but it's not as many as you might think are necessary to avoid problematic rounding errors. Now, in this particular case, probably because we started with relatively round numbers, all of the output calculations agree, which is fine. And so this is what I'm checking, right? Is the output different depending on which equation I use? And for the second trade, same thing. Excuse me. We get the same result all the way up to all of the digits that Python is allowing for. But in the third trade, now we're actually starting to see there's some disagreement between some of the functions that we're using. And this is probably a good time to consider, why does that disagreement come about? Because we've already shown algebraically that all of those functions are equivalent. And so it seems counterintuitive that one of them would be producing a different number to the other two. And this is why I said that you need to have a look at things like the IEEE 754 standard, because it will tell you how these numbers are stored and organized and manipulated in memory that will change the result that you're getting. So never confuse the calculation that you're doing on a computer with actual math, right? It's always an approximation. And so what we're really looking at here is which one of these functions implemented in Python gives, an approximation that we're happy to use. Now you'll see here that in the input information, I have a dx value that's negative, right? Which means that the trader is requesting some amount of tokens from the smart contract, which means that the calculation that we're doing is to output the amount of tokens the trader needs to provide to the smart contract in exchange. So if you like, dx is someone's trying to buy 123 cheeseburgers, and the cashier is saying, okay, this is going to cost you $604 roughly. But if we go down to these decimal places, we now find that actually, depending on which calculation we do, we get a slightly different result. And I'm choosing the most positive value here. Reflect for a second on why that makes sense. Why should we choose the most positive value. Because if the cash register says, oh, I'm getting 3 results, I will just give you the best rate, right? So we could have chosen the least positive value. And that would mean that our trader might actually get an advantage over the theory, that we would have rounded in the wrong direction, meaning if this was a malicious actor, they might actually guide the system into a certain point where they're always getting a good rate, buying cheeseburgers, selling the cheeseburgers back, and doing that in very large numbers of cycles until they have completely drained both the cheeseburger and cash inventory of the store. And this is a very, very common exploit, not just in concentrated liquidity dynamics, but also in just AMMs in general, and also in DeFi in general. So you need to always be extremely mindful of where your rounding errors are and in which direction they are. So in this case, I've implemented it so that of the 3 estimates that we've got, remember, these are just estimates, we charge the worst rate, right? So that the trader, even if they wanted to try and game the system, or at least in, according to this implementation, we generate 3 quotes and we give them the worst one, okay? And this is what's called defensive programming. Now, I don't want anyone to think that this is enough, right? Just having those 3 estimates and choosing the worst one is still not good enough to call yourself a secure programmer. You would actually need to throw away the IEEE implementation and implement these functions from scratch using integers only, right? Using fixed points. But that is, I think, a little bit out of scope for what we're talking about. And so within the confines of imagining that you have to use the Python standards as they are, I think that this is still demonstrating the point that I'm trying to get across, which is relying on just one of those functions might not necessarily be the best way to do things. And then after that, actually all of the trades that I performed in that sequence all had some sort of disagreement. I also want you to then think that if we're using the most positive value when quoting, the number of dollars that someone's getting, that we should also quote the least negative value when something is happening the other way around. So for example, when someone is inputting a positive number and we're trying to calculate how much tokens should be relinquished from the liquidity pool back to that person, that we should be giving them always the most conservative estimate, right? We never want to overestimate the amount of stuff that the trader gets, because that means that we are exposing an exploit vector and someone will figure it out and abuse it. Okay, I also prepared an animation. So you would have seen that in the Discord, I provided one of these frames as just a single sort of screenshot. But I think that the animation is also like very helpful in sort of getting your sea legs under you with how these kinds of mechanics operate. And there are a couple of details that I really want to bring your attention to. And one is that the direction of the integration across the price curve is important. So I'm going to pause this after we get to here. There we are. So features that I want you to notice. This red arrow on top, which is the amount of foo that is being traded into the curve, right? So this is a positive number. Obviously, it's pointing to the right to higher X values. So then, so the foo value is increasing. We can see that over here when it says the change in foo is 110, and then this blue arrow, which is the change in bar, is a negative value, right? Negative 500. Okay, fine. But have a look at the integrations that we're performing on their respective price curves. In the foo dimension, notice that this is color-coded to the other coordinate. So this price curve quotes d bar over d foo with respect to foo. So when you're integrating in the forwards direction here, this is like taking the positive of a negative number, right? Because remember, these prices are all negative. So it makes sense that the signed area of this integration is still negative, which is why this blue arrow is pointing down. Or if you like, the reason blue arrow is pointing down, or the negative integration here causes this blue arrow to be to be pointing down. Doesn't matter which perspective you take. These are two different perspectives of exactly the same calculation, which again is one of the things that I was hoping this homework assignment would try to crystallize for you. Now, what about the opposite integration? So we're starting at the at a different marginal rate. So notice that this is the reciprocal of d bar d foo. So this is d foo d bar, and we're integrating backwards, right, from high values of bar to low values of bar. Now this means that because the integration is being performed in reverse, this is actually a negative of a negative. Right, this is already a negatively signed area, and we're performing it backwards, which means that this is a positive area now, which is why this arrow points to the right. So what's interesting here is, or maybe not interesting, but what might be confusing the first time you engage with this kind of this kind of differential analysis is that the blue arrow, right, the amount that we move in the negative y direction, you have to integrate with respect to the x direction and the appropriate the appropriate marginal rate formula. And the opposite is true for bar, right? If we want to get the amount of bar, right, so the length of this red arrow, then we need to make sure that we are integrating again the correct marginal rate formula with respect to bar. So the amount of foo, right, that we are moving across here is calculated with respect to bar, and the amount of bar we get in the y dimension here is calculated with respect to foo. And if you've done calculus fundamentals recently, you might be rolling your eyes at the obviousness of that. But I do appreciate that some people haven't done this kind of stuff in a while. And that might seem counterintuitive, and that's a very easy mistake to make when you're actually doing this kind of stuff for the first time. Now, just quickly wanted to make note here that the fact that both of these price curves are the reciprocal of each other is, in a sense, a design choice, right? We are forcing both of these price quotes to be dependent on each other, but does it have to be that way? Right? Did we necessarily need to derive both the forwards and reverse price quotes from the same implicit curve? And that was a very important, the answer to that, by the way, is no. And this is what led to the development of carbon. Now, we're not going to discuss that in this lecture, and certainly it's beyond the scope of the homework, but we will be returning to this in lecture 4. Which should, I think, give you at least a signal that I need you to be really on top of these concepts by the time that we get there. So if you feel like you're lagging behind, again, contact me. We'll do the office hours. We'll make sure that everyone is up to speed. Okay, that concludes our homework discussion. I will upload the code for how I generated those animations to the GitHub after this lecture. Okay, lecture 2. We've got a long way to go, so, oh, yes. Oh, yeah, we were going to have a brief discussion about this.
Can we try to let Maya ask her question again?
Do you hear anything?
I can hear you. Oh, Maya's all questions solved, all questions answered.
Okay,
Just
great.
dropped a message instead. Thank
That's
you so much.
well, that's a happy ending. Okay, let's move on with, okay, lecture 2. So everything that I just discussed is revision of lecture 1. And so if you, like I said, if you feel that made you uncomfortable and that you don't yet have that level of erudition, again, contact me, we'll figure it out. If you're in that position, I suspect that some of this lecture is going to be a little bit stressful, but I have made a deliberate attempt to bring in some heuristics that I haven't used before based on some of the conversations that I've had with other students during the office hours. Now that's added a little bit of time to this lecture, so it is going to be a long one, but I'm confident that it will make some of the material a little bit more accessible. So I thank you in advance for your patience, and I apologize if you feel it's unnecessary. But again, I'm trying to cast a relatively wide net with respect to the level of mathematical ability that each one of our students has. Okay, Recall that we did this process in the first lecture. We started with an empty Cartesian plane. We selected a point, and then we defined this invariant function, and we drew that function's implicit curve through that point. And it will necessarily pass through that point. There's no way that you can get around that. We then took that implicit function, the invariant function, and we did a couple of trivial rearrangements just to show that you can express y and x in terms of the invariant, or you can express x in terms of the invariant and y, or y in terms of the invariant and x. What we're going to do today is to take those starting coordinates and then multiply them by some constant, right? And so this is going to be, it's like x0 and y0 in the sense that it becomes a part of the invariant function. So we take that constant a and we multiply both of the token balances by that. And this creates what are called the starting virtual token balances. And then we do the same thing as before. We draw a rectangular hyperbola through it by defining this invariant, which is, if you squint hard enough, you will realize it's actually exactly the same curve as we've drawn before. It's just that now the invariant is larger, and I'll demonstrate that, I think, a little bit more explicitly in just a minute. So this means that we can factor out a, or just combine those terms into a squared, I think is a better way to say it. And then we can actually perform the same processes as we did before. But before we do that, note that these x and y coordinates no longer refer to actual token balances, right? You can't just pretend that you've got more tokens. No one can create a liquidity pool and say, okay, now multiply my token balances by 10. Otherwise, people would just do that ad infinitum. And, we'll just be printing, tokens out of nothingness, which, depending on your perspective, might be what cryptocurrency is doing in general. But specifically for exchange algorithms, it's really important that you don't just duplicate tokens. So I'm using subscripts v to indicate a virtual coordinate, which is deliberately to delineate it from actual x and y, right? From real coordinates. And I've used that throughout the textbook that I've written for you as well. And so I'm going to use that same nomenclature, that same convention in the presentations. Okay. So now that we've got our curve, note that we can do exactly the same manipulations that we've done before, right? There's nothing really new about this. We can still express y and x in terms of each other in the invariant, or in terms of just one of the others in the invariant. Now, what this means is that we can also come back to all of the swap equations that we've already defined, and remember the ones, there are some in here that I didn't present in the last lecture, but that you can derive, and that we presented during the homework discussion section. And then we can basically just substitute the old invariant for the new one, right? So instead of x0 times y0, we're now going to substitute that for a squared times x0 times y0. And now we get all 6 of our swap functions for the virtual curve, which is pretty convenient. Now you can go through and derive them all from first principles, the way that I did in the first lecture. But this shortcut is actually totally robust, right? There is nothing that you would consider, there's nothing here that would be questionable from sort of an algebra perspective, right? This really is a one-to-one substitution. And so that means that we now get 6 reference equations, and we can start doing manipulations with them. And again, the only the only difference between the equations that you've just seen for the standard curve and this one is that we've multiplied everything by a squared. Okay, so where to go from here? Why would we do this at all, right? What would motivate someone to create these virtual token balances, and what are the ramifications? Why has this had such an impact on the way that we think about liquidity models in cryptocurrency? I think the best way to get a grasp on this is to briefly forget about the amplification that we've just spoken about, and instead just focus on 2 liquidity pools. And we're going to say that both of these liquidity pools contain the same tokens, right? We're going to use foo and bar again. Now, the red liquidity pool, the one on the left, we're going to give 100 tokens of each of these things. And the liquidity pool on the right, we are going to give 10 times that number, right? So it's got 1,000 of each token. Now, important to realize that however you do it, you're going to find that both of these liquidity pools, despite the difference in their token balances, are actually quoting the same marginal rate on both, okay? And that, again, should not be surprising because you know from last lecture that it's the ratio of the token balances that matters and not necessarily their absolute quantity. But what does change is the effective rate, right? Remember, the marginal rate is just a price quote so long as you trade zero, right? If you like, it's the effective rate when you trade zero tokens. But when you're trading a non-zero amount of tokens, the marginal price doesn't really matter anymore. And what you really want is the effective rate. So let's simulate a trade, right, on both of these liquidity pools. We're just going to choose one of the swap formulas. It doesn't really matter which one we choose. And we're going to say that some trader is trying to swap 25 of the foo tokens in exchange for some number of the bar tokens. So if you like, you can substitute out the X and Y for the actual token names. For some people, this is helpful. Other people prefer to abstract things back into X and Y coordinates, to each their own. Okay, so pushing 25 into the formula, and then substituting each one of these liquidity pools token balances for the remaining foo and bar coordinates gives us these expressions, which simplifies to these expressions. And just running that division will give us a slightly different result for both. Well, maybe not so slightly. On the left, we're getting a D bar calculation of -20, whereas on the right, we're getting a D bar calculation of -24.4. And that's, roughly a, like a 5% difference. So my question is, which offer is better for the consumer, right? We are talking about a person, right, who's interacting with these liquidity pools. And they are saying, I want to send 25 foo tokens to a liquidity pool in exchange for in exchange for some number of bar tokens. Put yourself in that person's position. Would they rather get 20 bar tokens in exchange, or would they rather get 24.4 bar tokens in exchange? Clearly, the blue liquidity pool is giving them a more attractive rate, right? They are actually, they're getting a better price, right? Note that it also means that the liquidity pool is getting a worse price, right? So from the perspective of the consumer, if they're getting a good price or something that they're happy with, it's always going to be the reciprocal of what the liquidity pool is getting. But that's neither here nor there, just a question of perspective, and we'll continually return, I think, to this topic over the course of these lectures. Now, imagine that the red liquidity pool is like somehow sentient and decides to do something about this, or they can anticipate that this trader is about to perform an action, and they're going to change their pricing algorithm, okay? So the red liquidity pool, in order to attract that consumer, says that I will price match my competitor. And this is not so alien, right? I'm sure that we've all been in that situation where you're at some sort of department store or something, and they will have either a promotion or even just a store policy that if you find a better price at one of their competitors, they will offer you the same price. I'm just asking you to imagine that situation here with a liquidity pool. I don't want you to think that this is how concentrated liquidity works, because it's not, but it's that same idea, is how can a smaller liquidity pool compete with larger liquidity pools? The only way it can is by offering a better price. So now imagine the red liquidity pool says, I'm going to give you exactly the same rate. Now the consumer can choose, right? It doesn't matter which pool they choose from. They're going to get the same rate of exchange. Now imagine that this isn't a one-off, right? rather than constantly price matching, that red liquidity pool can just come to the determination that they should always price their tokens as if they were a 10x larger liquidity pool. And that's an interesting realization, right? Because like I said, with respect to department stores and, like consumer electronics and white goods and things like that, this is already a sort of like market dynamic that we're familiar with. And you should also be aware that that kind of pricing structure leads to bankruptcies. Some people, some businesses simply cannot offer the same prices that their competitors are. And when they try to, they fail to meet their overheads, they can't pay their bills, so on and so forth. Which means that this blue liquidity pool hasn't actually lost any of his advantage, because at the same time as this red liquidity pool is saying, oh, I can just offer the same prices that you are, he can also just offer 10% of the liquidity that he has and also offer the same prices. And this means that he's not as levered, right, as the red liquidity pool is. The red liquidity pool is offering all of their capital in order to compete. And the blue liquidity pool is saying, fine, if you do that, I'm just going to offer 1/10 of my liquidity, and I'm still going to get the same consumers that you do. So don't ever make the mistake of thinking that concentrated liquidity has somehow leveled the playing field or any of this other bullshit. It's exactly the same market dynamics as has always existed in any capital market. Okay, so the short version is this, right? Regardless of your perspective on market dynamics and leverage with respect to some reference price model or whatever, the point of our course and the theory that we're examining is that it is possible to rework the pricing algorithm to allow any liquidity pool to emulate an arbitrary size. That's the only important thing, right? Where this isn't an economics course, this is a concentrated liquidity and pricing mechanics course. So the question is, what is the catch? If this red pool is always offering a price that is equal to a competitor 10 times their size, surely, right? There's something's got to give. It can't just do that free of charge. There are no free lunches. To understand how this works, we need to consider exactly what this means. So this is the system that we're setting up. On the left, we have the real token balances, which is again just 100 and 100. And here I've replaced the foo and bar for X and Y. And then we've got the virtual token balances, which is 1,000 and 1,000, because we're applying an amplification term of 10. This is also called the capital efficiency term. And you'll see this described in a couple of different ways. I really hate the term capital efficiency term because it gives the impression that it has something to do with capital efficiency, which it doesn't. So I prefer things like amplification coefficient or leverage coefficient or something like that. But again, even then, leverage suggests that there might be a loan or something involved, which isn't the case either. So let's just go with amplification coefficient, because I think it's the one that's like closest to the metal when it comes to how these pricing algorithms were actually developed. Okay, so we've got a certain swap amount, which is that delta x equals 25, the same that we had a look at before. And we calculate that on the virtual pool every time, right? So when we offer a trader a quote price for the tokens that they're trading, we first multiply all of the reserve balances by 10, give them the price, and then the trader can decide to take that price. So let's say that they've done that. They say, great, yeah, I like that. Here's my 25x tokens, and the liquidity pool gives them the 24.4 Y tokens. But those aren't virtual tokens, right? Traders don't trade with virtual tokens. Traders only trade with real tokens, which means that delta X and that delta Y is applied to our real token balances, right? We didn't mint tokens to give them. They can only come from the token reserves that we actually have, not the ones that we're pretending to have. So after we compute the trade value on the virtual side, whatever those token exchange amounts are, apply them verbatim to the real token balances, no exceptions. Now, one of the things that you'll notice right away, right, is that now that you've just become comfortable with the sort of the constant product liquidity invariant function, is that that's now completely thrown out the window. Because if we multiply the two starting token balances by each other and then the two final token balances by each other, these things are not equal, right? So the general invariant that we had before is no longer true, right? And we need to determine a new one. Okay, now I want you to imagine what happens when we offer a price that would drive one of these tokens to 0 in the real case, right? So in the virtual case, because it's a standard rectangular hyperbola and behaves exactly the same as the stuff that you did in last week's homework assignment, you can never drive the virtual tokens to 0, right? Those will always be asymptotic at 0. But not so on the real tokens. So after we apply that trade to the real token balances, our Y tokens are now driven to 0 and our X tokens are at like 211.1. So this is important. Just because the virtual tokens can't be driven to 0 doesn't mean that the real tokens can't. And the reason is because we're offering a pricing algorithm that is pretending to be larger, right? So there is a point where at the virtual token balances where this pool will simply cease trading, right? It is no longer possible for a trader to take tokens out of the real pool, even though the virtual pool is still saying that it's got 900 tokens left, right? Because those 900 tokens are fake tokens. The real tokens, the 100 Y tokens that were there, are now gone. Okay, what does that mean? We still take the marginal price quote from the virtual curve, right? This is the pricing mechanic that we're using. We're still emulating a larger curve. In a way, the red pool is just saying, I will use the same price quotes as a pool 10 times my size all the time. But that doesn't change the price quote when we go back to the real token balances, right? Because in a way, it's always offering the same price. So that means that there is a dy dx value or a dx dy value where the marginal rate beyond that point is impossible to reach now. And the reason for that should be simple, or should be simple to understand, because we simply cannot get to lower Y token balances than this. So this is a hard limit on the price quotes that this red pool is able to support. So if that's what happens when the Y token balance is driven to 0, what about when the X token balance is driven to 0? So we're going to perform another trade. This time we're going to be swapping Y tokens into the pool and pulling out all of the X tokens. So again, on the virtual curve, this doesn't look like it's a problem at all. Its virtual token balances are still non-zero. But when we apply those amounts to the real token balances, there are no X tokens left. We've essentially exchanged all of our X token inventory now for Y token inventory, which means that when we perform that same marginal rate calculation on the virtual curve, we can apply that verbatim to the real curve and we get a different price bound. And these are important terms. These are the prices of of Y with respect to X, and you can do it this if you want to take the reciprocal and quote it the other way around. That's also fine. But the point is that our red pool that is amplified by some coefficient is going to be bounded between two different price quotes, and that's what we've just shown here using sort of a heuristic model of of actually amplifying this thing out and having a look at the virtual and real token balances. So in short, any dy dx value below 8.1 and any dy dx value above 1.23 is unsupported. That means that one of our token balances is driven to 0 and no one can trade beyond that point. Now, there is a convention that I do like, right? So this is one that the industry has largely used. I'm going to use a slightly different subscripting nomenclature, but the idea is the same. And that is that I'm going to use the terms P high and P low to refer to the absolute value of this thing, right? So if dy dx at one of these bounds is negative 1.23, then let p high be 1.23. Get rid of that negation. Now, this is, again, this is just like syntax sugar, right? It doesn't change the meaning of anything that we're doing. It just means that some of the calculations just become intrinsically easier to do and easier to write down. And, you know, in general, I'm kind of a stickler for keeping negative signs when they, you know, when they're important to demonstrate. And I've already told you how I feel about it in the first lecture. But in this particular case, dealing with the absolute values of these numbers is, it uncomplicates so many of the calculations that there's really no reason to not doing it. So just remember how I've defined this, right? In a way, the P high and P low are the negated values of dy dx, right? Or of dx dy, depending on your perspective. And so when we set negative p high to be dy dx at one of the price bounds and negative p low to be dy dx at the other price bound, then that negation simply cancels out and we can quote them as positive numbers. So it's not necessarily an absolute value. Like, obviously we're deliberately making it a positive number so that it's easier to calculate with it. And this is helpful because we're going to be doing things like square roots and other things, but just know that we didn't actually take an absolute value. We're actually deliberately assigning p high and p low to be the negative of the marginal price formula. So it's not an absolute value. It has a precise definition. I have covered this ad nauseum in the textbook material that I've written. And so if you ever get confused about how this convention works, go back to the book and read it from there, or approach me for an office hours and we can uncomplicate it there. Okay, so the purpose of that part of the lecture was to give you what I hope is what I call a heuristic understanding, right? You kind of, you know, by watching these animations and hearing how I speak about it and seeing the numbers, you know, can kind of give you this sense of like, yeah, I can see how that mechanism is working, or you know, I understand that when token balances are traded out of the real curve, it's possible to drive them to zero and we can get a marginal rate and so on and so forth. But one of the things that I think you need to appreciate about designing protocols, or even just understanding protocols, is that you cannot do everything numerically. And if anything, the demonstration that I had at the beginning of this lecture is testament to that, because you can never trust the calculation that you get out of any computer. The only way to actually properly internalize the system that you're designing is to do it symbolically, right? Is to do it algebraically. Because that is the only way that you get infinite accuracy, is when there's actually no numbers involved. And so that's what we're going to do right now. We're going to go through that process, but geometrically and algebraically without reference to a number at all. Okay. So this is basically where we left off before we started that heuristics discussion. We started with an x coordinate and a y coordinate, which is the x0, y0, and then we amplified it by some amount by multiplying each one of those token balances, starting token balances, by the amplification coefficient A. Then we drew this curve through it, which is our new invariant. But remember, this is the virtual invariant. I should have used the subscripts xv, yv at the top there, but that's okay. Okay, now, when I said that the real curve still only has a certain number of tokens available to it, right? It only has x0 tokens there. What I'm drawing with this shaded region is basically showing that if we pull that region all the way back to zero, right, that is the sort of x0 minus x0 amount. If we want to know where the bound is on the orange curve, right, on our amplified curve, our artificially amplified curve, we just perform that same process, right? These two vertical bars are necessarily equal in width, and their width is x0, right? Whatever the initial token balance on x was. And so where that vertical bar from a times x0 pulled to the left, that will give us a new coordinate, right? So we want to contain that vertical bar, you know, between these 2 points. And so we're trying to find the coordinate where the curve is like leaving that region. That's where we're running out of X tokens. Now, as I just said, the X coordinate there is going to be A times X0 minus X0. Hopefully that's not controversial. And the Y coordinate for it is just going to be applying a rearrangement of the invariant function that we derived earlier in this lecture. So we just take the invariant, which is a squared times x0 times y0, and divide it by whatever this new x coordinate is, which is a times x0 minus x0. Now that is not the, I don't think is the best way to write these equations down, because you can factor out a common term in both cases. So what I've done in the top is to factor out x0, which means that it cancels with the x0 on the top. And in the bottom, again, you can factor out x0 as a common term, which leaves us with x0 times a minus 1, which is a little bit more compact and certainly a lot easier to wield algebraically. Okay, so that now gives us the literal coordinates of let's say the maximum y balance and minimum x balance with respect to the virtual curve, right? This is the point where our real token balances, at least on in the x dimension, have gone to 0, but the x coordinate in the virtual curve has not yet gone to 0, just like we saw in the heuristic model.
We have 2 questions.
Oh, yeah, please.
2 questions.
Hello, can you hear me?
I think Tiago was first.
Can you hear me?
Can you hear me?
Can you hear it?
No, can you?
I can hear you.
Hello.
No, I can
Give us a moment.
Oh, you know
Tiago.
why? You know why it is? It's because I muted. I know exactly why it is. Okay. Okay, try again.
Hello?
Yes, I can hear you.
Yeah, thank you. So maybe this question is a product of my lack of calculus and math, but in the previous example where you were explaining how to know the P high and P low, why is it necessary to simulate all the potential traits in quantities to know this P high and P low? Because, well, from the example,
absolutely
you
not. And yeah, I'm actually gonna show you here. So we're gonna do everything algebraically now. So we're gonna go through all of these steps, and we're not gonna bother simulating anything. And we will define the algebraic identities for every single one of these things.
Okay. Thanks.
No problem.
I don't know if you can hear me.
Mhm.
Hello? You can?
Yes, I
Okay,
can hear
awesome. So this is more about like the amplifier itself. Like I was curious to understand if it's actually like a parameter for the liquidity pool that you're in, or like the actual liquidity provider can, set how much leverage, that is, how much amplifying he wants for his own liquidity. And then
Yeah.
if that happens, like there could be like several bonding curves at the same time in the same liquidity pool. Is that the
Correct.
scenario?
Yes, that is absolutely the scenario. So it depends on the implementation. So we will, I will start discussing this in more depth when we get into it. So in the Bancor V2 case, which is actually the model that we're discussing right now. So this is the description that was laid out in Bancor's like 2020 patent. This is the construction that I'm simplifying it a little bit because it also had like another sort of mechanic in it that was designed to keep everyone in a single liquidity pool, which was, it was a complex design. We decided to discontinue it. Uniswap v3 came about a year later, and what they did was instead they implemented a system that has a very large number of liquidity pools, all with some defined price boundary. So these are called tick ranges. And when you are providing liquidity to something like Uniswap v3, you choose your like level of amplification by choosing the price range over which you will contribute your liquidity. So if you put all of your liquidity in a very small price range, that's akin to putting like a lot of liquidity inside a very, very amplified bonding curve. Whereas if you distribute your tokens over a few more of these things, then you get, like less amplification. But then each user, when they're interacting with Uniswap v3, is choosing which buckets they want to provide liquidity to. So you still get the agency, I suppose, of like how amplified you want your liquidity to be with respect to the price ranges that you deposit to. But at the smart contract level, it really is just like I think 2 to the 256 different bonding just provide tokens to the liquidity pools that they lack. And in a way that a totally reasonable abstraction for how blockchain, finance works anyway, because it's not like there was ever one liquidity pool, right? Liquidity is necessarily fragmented. There are lots of forks of different liquidity pool systems and different, innovations and iterations on top. That means that even if you tried within your own implementation to give everyone access to one single liquidity pool deployment, someone else is going to have a different one. Someone's going to try and compete with that structure. And now you've got 2 different liquidity pools. And, the process just continues and continues. And so when we did Carbon DeFi, and again, this is something we'll discuss in lecture 4, we decided to, there's no point anymore in trying to get everyone to pool their funds together. So the concentrated liquidity pool that we have, the concentrated liquidity implementation that we have in Carbon DeFi has no liquidity pools at all. And every single user has defines their own amplification individually without reference to an existing liquidity pool infrastructure. And this means that with Carbon DeFi, there are things like no tick ranges, and we can also separate the bidding and asking prices and other things that we'll get into later on in the lecture series. But the short answer is that with respect to the theory, yes, it's absolutely possible that everyone can choose their own relative amplification, and we can just have an arbitrary number of different bonding curves running all the time. In practice, it depends, right, on specifically which concentrated implementation you're talking about. In Uniswap v3, they try to organize everyone into rooms. In Carbon DeFi, we say, screw it, like everyone can do whatever they want. And there's no right or wrong choice. And I describe this in the textbook, by the way. It just depends on like the architect decision on how that system should operate and like what objective it's trying to meet, how things should be organized and maintained. But at least in theory, it's irrelevant, right? This level of abstraction that we're speaking about now, just let everyone have their own amplification and then let there be an unlimited number of bonding curves. Have I articulated that well?
Yeah, that was very insightful. But then just to conclude, so like when a liquidity provider goes to the dApps GUI on Bancor, for example, what does he define? Does he define the A amplifier or just the price range? Or he can edit both at the same time?
Yeah, I can. I don't want to show the. Actually, you know what? Why don't we just? Yeah, actually, I can't do it from where I am right now, but yeah, essentially they define the price range, and the price range and the amplifier are actually one and the same thing. Just like how you and I spoke about the the slippage and so on all being sort of contained within a single expression, and you get slippage and effective price together as like one and the same thing. Amplification and the price range over which you can service the market are also functions of each other. So defining the price range is the same as determining the amplification coefficient. It just depends which one you want to be a function of the other.
Okay, so you can define either both of them. So it's up to the liquidity provider.
It's up to the liquidity provider to decide what they want to do, but it's up to the architect, right, to the smart contract engineer and the product architect to decide which functions we're going to use.
Okay.
And
okay,
this is where the engineering becomes important, because what I'm showing you here is that all of these things are mathematically equivalent, right? Where the process of liquidity amplification that we're discussing today is going to be exactly the same as the one that we discuss next week. It's going to be exactly the same as the one we discuss the week after that, and even the week after that. So they're all mathematically and algebraically and geometrically identical, but we have all of these different versions of it. And there are good reasons for each project to be using different functions. Just like in the at the beginning when we did the homework discussion, I showed you that some of those swap functions actually disagree with each other, right? Because of the limitations that we have in precision and accuracy in the IEEE 754 standard. So there is, it depends on what your product is trying to accomplish. You shouldn't think that, all of this theory is going to be equally applicable, right? And all of these equations and functions that I'm showing you are equally good in all circumstances. That's absolutely the wrong way to think about things. And unfortunately, it's a misapprehension that the industry seems to have, malignantly adopted. What is much better is that you understand that these things refer to the same thing in theory, and then understand that each one of these implementations has a different accuracy and precision cost, right? It's always a trade-off. You need to find the thing that does what you need it to do in the context that your product lives in, rather than take someone else's implementation and then try and wrap a product around it, which is the mistake that I think a lot of developers are making today.
Perfect. Thank you, man. Thank you.
You're welcome. You are welcome. Okay. Let's continue. We've got about 25 minutes left, which I think is going to be enough time. Okay, so this is where we got up to. So we've looked at our old invariant, which is the gray curve, and our new virtual invariant, which is the orange curve. And so far we've deduced what the virtual coordinates are when the real token balances are going to 0 in the X dimension. What about the Y dimension? Well, the process is exactly the same, right? We start with Y0 tokens, which means we only have Y0 tokens to sell. And so whatever that vertical distance is between Y0 and 0, which is of course just Y0, we have to subtract that from our starting virtual coordinates. And if our starting virtual coordinates is A times Y0, then the limit of the virtual coordinate, the Y dimension, should be A times Y0 minus Y0, which simplifies to Y0 times A minus 1. So now we've got both the X and Y coordinates on the virtual curve for the, for the virtual token balances that we are actually allowed to use. Okay. So taking some of those things away, what I want you to see here is we've actually got 3 points that we've identified on the virtual curve, and these have all been deduced from just one point on the what I call the reference curve, right, on that original invariant function. And what we're going to do is we're going to try and understand the amplification process through the lens of the marginal rate equation, right? We're going to look at how much more trading activity can you get for the same relative change in price. I'm going to map that back to the reference curve because these are also algebraically and geometrically interesting points. And as you'll see in lecture 5, it has a very, very profound influence on the hyperbolic trigonometric analysis that we're going to perform at the very end of this lecture series. Okay, so here I have taken the high point, right, the highest y and the lowest x value on the virtual curve, and I've drawn a tangent line to the curve at that point. And this is, in a way, the definition of the marginal rate. And for this analysis, and I think almost all of the analysis that I do, I'm always going to take the perspective of y over x, like this is the way that I quote things, but just know that it's arbitrary, right? This can be, as you've seen, d versus d bar, you can do x versus z, you can do whatever letters that you want. But with respect to making sure that we've got a convention that is at least serviceable for the rest of this course, just know that I'm always taking the vertical dimension as a, or doing the derivative of the vertical dimension with respect to the horizontal dimension. Okay, so we know how to calculate dy dx, or the marginal rate, because it is the y coordinate divided by the x coordinate, right, or the negative of that. And so what I've done is to negate this process, or negate that already by taking the negative derivative. And all I've done is to substitute the y coordinate and the x coordinate into our marginal rate formula, right? Which is that a squared times y0 over a minus 1 divided by x0 times a minus 1. And after, a bit of simplification, that gives us this a squared over a minus 1 squared times y0 over x0. And so that actually is the marginal rate at that point. And so as Tiago was just expressing, is like, do you even need to perform like these swaps in order to get there? The answer is no, right? All we need is the algebraic identities for that coordinate, and then we can apply the marginal rate formula in order to get the price bound. Okay, and since this is the price bound with the steepest slope in terms of y over x, I'm going to give this a specific name that refers to that attribute in just a moment. Now we can do exactly the same process for the other point. So again, here's a tangent line. It is at the point that we've already identified on the virtual curve where we have run out of y tokens. So we still have a non-zero virtual y, but the actual y that we can trade with has been depleted. And so we're interested to determine what the price bound is there as well. And it's exactly the same process, right? Marginal rate formula as before. We take the y coordinate over the x coordinate. We've already worked out that the virtual y coordinate there is y0 times a minus 1. We've worked out that the virtual x coordinate there is a squared times x0 over a minus 1. And by simplifying that, we get what kind of looks like the reciprocal of the term above, but it's not quite, because we still have y0 over x0 as a factor, but the coefficient has been reciprocated. So instead of a squared over a minus 1 squared, we now have a minus 1 squared over a squared. But great, now we actually have algebraic descriptions, not just for the x coordinates and y coordinates at the price bounds, but also the price bound itself, without referring to a single number, without having to simulate any trading or anything like that. These have all been deduced just geometrically. Okay, so this is kind of the summary of what we've got. And just appreciate for a minute that, we're already piling up like an enormous amount of information here. And this is going to be, I think, a consistent feeling that you're going to get throughout these lectures, right? For people that haven't had a look at the PDF that I prepared is kind of like an overview of the lecture series. It has something like 330 equations in it, and I'm not going to present every single one of them, but we necessarily need to present a lot of them. And I think the only way that you can maintain familiarity with what these things mean is by actually using them, right? Which is why I assign these homework assignments and actually get you to engage with it in some other way than just reading it on a screen. Sometimes the only way to learn something is to actually do it. Okay, so I refer to these two marginal rate formulas as P high and P low. You'll see people refer to them as PY and PX, or PA and PB, and so on and so forth. And there's no real agreement on what these things mean. And so I'm using the subscripts high and low because I think that it is a little bit more intuitive which one we're referring to. But just know that if you read it elsewhere in the DeFi literature, they may have a different subscript or even a different symbol, but means more or less the same thing. Okay, so now that we've got these tangent lines to the virtual curve, I want to ask the question, where are those same price bounds? Like, what would be those prices on the reference curve, right? On the curve before we amplified it. Okay, and so I'm now drawing gray tangent lines, and hopefully you can see those. I understand they might be a little bit pixelated. But these are lines parallel to the tangent lines that we've just drawn for the orange curve, and also tangent to the reference curve. And this is uniquely defined. It is enough to say that there is a parallel line somewhere on the reference curve that's also tangent to the reference curve with respect to the tangent line we drawn for the other one. There is one unique point there. And so what we want to do is find out where those unique points are. And luckily, we already kind of know how to do this, right? And this is the shortcut method. And that is to observe that if the virtual token balances are amplified by some constant A with respect to the reference balances, then to get back to the reference curve, all we need to do is divide through by that constant A. There's a more robust way to do this. It's a little bit more rigorous, And I actually go through that process in the paper that I've written for you guys. But just know that this is a very fast and very convenient method to do it. And I think it's the most intuitive, and there's nothing wrong with it. It's just a little bit abstract, but it's also, you know, fast and convenient. So if we take that y value, right, of the y coordinate on the price bound of the virtual curve, which is the a squared minus y, a squared times y0 over a minus 1, and divide all of that by a, then we just get a times y0 over a minus 1. And so what we now have is the y coordinate at the point on the reference curve that has the same marginal rate as the literal price bound on the virtual curve, right, where we're actually running out of token balances. And we can do the same process to get the x coordinate. If we already know the x coordinate for the virtual curve at the price bound is x0 times a minus 1, then we can just divide by a to get its x coordinate. And then the process is exactly the same for the other price bound. If we know that the x coordinate at the low price bound is a squared times x0 over a minus 1, then just divide through by a, you get exactly the same, the same sort of algebraic description of the of that x position, and then we do the same thing for the y position. And so now we've managed to sort of further decorate our curve. Now, with coordinates on the reference curve that have the same marginal rate as the points on the virtual curve, where the token balance for the reference curve would be running out if it was amplified. And so this is, I think, a very helpful visualization for what the amplification process is actually doing. Because what we're doing is we're taking a reference coordinate around the reference curve, right? The x0, y0 point, drawing a rectangle around it, and then blowing it up onto some other curve. Think of this as like holding a candle in a room and then holding an object in front of it so that its shadow is cast on a wall across the room, right? And the further that wall is from you, the larger the shadow is. And that is what this is doing, right? In some respect, it's exactly what this is. You can think of the virtual curve as being the reference curve's shadow around some point at some distance away from the light source. And that distance away from the light source is proportional to the amplification coefficient. Okay. Now, we need to do something. We need to do a maneuver now where instead of using the virtual token balances all the time, we now would rather just know what the real token balances are, right? So rather than go through this process that's kind of awkward of maintaining virtual token balances and then constantly referring back to real token balances, which is going to occupy a lot of space in memory, right? Which is going to allow for errors to compound in a really dramatic way. And there was a concentrated liquidity protocol, by the way, that was implementing it exactly this way. And they were hacked for $85 million just recently. So it does make sense to think about removing as much of the unnecessary steps in your math as possible. And what I call this step is creating the real curve, right? So if that reference curve is the one that we're amplifying to create the virtual curve, then the real curve is the one that we then drive back to the X and Y axis so that we're no longer dealing with virtual token balances and we're only dealing with real token balances. This means that we're much, much closer to the source of the information that we're actually dealing with, and means that things like those rounding errors that I was showing you earlier in the homework discussion, there's far fewer steps for those kinds of things to go wrong. And even if you're very, very clever and you're a very experienced engineer, the more stuff that is happening when you're calculating something and the more variables that need to be managed, the more likely it is that you are going to encounter an exploit at some point. We call this the attack surface area. So what you want to do is keep the attack surface area as small as possible, which means that you generally want to have one equation that describes as much as possible rather than equations and functions handing off things to other functions and so on. Okay, so it's basically this. We want to drag that orange square down so that its leftmost corner, right, the bottom left corner, sits exactly at the origin, which means that the points at the price bounds are going to sit on the X and Y axis. Okay, how do we do that? Oh, before we speak about how to do that, just know that that whole process is equivalent to just dragging the square around the reference coordinate that we started with before amplifying it, and just deciding to drag two of its points towards the X and Y axis. This is actually a redundant description. It's just that this one is actually more difficult to describe. I have done this. I've done a similar lecture series on concentrated liquidity for the bonding curve research group. That's also on YouTube. But that transformation of like dragging the corners out to the edges is much more abstract. This process of amplifying and then moving the amplified curve around, I think, is a little bit easier to engage with. Okay. So how do we actually perform this translocation or this transformation of the virtual curve back? Well, we already know that the virtual curve has this invariant, what should be xv times yv equals a squared times x0 times y0. And one of the things that you may recall, and this might be from a very, very long time ago, but when you were studying like parabolas and things for the first time, you might recall that you can add horizontal and vertical shift components to your equation, and this will like move things around like on the Cartesian plane. And that's exactly what we're trying to do here, right? We take the virtual curve description and we modify the X and Y coordinate by a horizontal and vertical shift to reposition that virtual curve around the origin so that we no longer have to refer to virtual tokens, and instead it maps one-to-one with the real tokens. So what are those horizontal and vertical shifts going to be? You can see on the plot, I have annotated these white arrows, which show you that what we want to do is to take that leftmost X coordinate, right? The X coordinate at P high, and we want to drive that to the Y axis. And so in order to do that, well, we need to remove x0 times a minus 1, right? That is the X coordinate of that position. And so that is the horizontal shift component. What about the Y dimension? Well, it's exactly the same thing. We've already algebraically determined that the Y coordinate for the point at P low is y0 times a minus 1. And so if we want to drag the hyperbola down towards that axis, we need to subtract off y0 times a minus 1 from that Y coordinate. And so these are, these are the horizontal and vertical shift components that we've been looking for, right? Nothing too complicated there. And so in order to generate the real invariant, right, the thing that actually does remain invariant under the swaps that we've been discussing, all we do is we take the virtual invariant and then add these shift parameters next to X and Y. And that's how this equation is produced. Okay. Now, it's important to realize, and I apologize for how close some of these coordinates appear, but you can see that this does become a very crowded plot if I'm trying to maintain all of these annotations. But just remember that I've color coded it. So this x0 times a minus 1, this is the coordinate for like the leftmost edge of the orange box. And this y0 times a minus 1 is like the bottommost edge of this orange box. But what I really want to know is, or right now that we've got this equation, is what is the topmost edge of the blue box and the rightmost edge of the blue box, right? These are really important coordinates, and they have some properties that make some of the algebra and geometry a little bit easier to handle, and we can derive a lot of really great relationships from these that enable us to create all kinds of interesting analyses. And it's also going to tell you the maximum number of Y tokens and the maximum number of X tokens that you can have if the market decides to take all of one of your token balances away. Okay, so this is the part that we want to get to. Now, there are a couple of ways to do this. And because I am aware that this lecture is a little bit long, what I have done here is to just, I've added this x equals 0 at the top of this curve, is that if you just take this expression, right, and substitute x for 0, and then rearrange it for y, you will get this term. Right, and I was unable to animate this because it takes me a little while to animate these things, and so I'm just annotating it here for you. But it's maybe something that you should do on your own. Right, take that function, substitute x for 0, rearrange it for y, and see what you get. You should get y0 times 2a minus 1 over a minus 1. And if you evaluate it at y equals 0, so in this case, we're taking the y coordinate, substituting it for 0, and then rearranging for x. You will get pretty much the same expression, except now it's x0 times 2a minus 1 over a minus 1. And these are also important coordinates. Okay, high level. We've got 3 curves. The gray one we call the reference curve, the orange one we call the virtual curve, the blue one we call the real curve. And I need you to know about all 3 of them and their algebraic and geometric descriptions. We've already identified 3 important points on the virtual curve. Obviously, the midpoint, which is the just the x0 and y0 reference point that we started with, amplified by some amplification coefficient. And then we identified the x and y coordinates at the high and low bounds, right? When the real tokens are being driven to 0, or when the marginal rate is equal to p high or p low. We've also characterized the points on the reference curve where those rates, those marginal rates, are the same, right? So obviously at x0 and y0, it's going to be the same as a times x0 and a times y0, because the a's will just cancel out when you apply the marginal rate formula. But we've also deduced that at the price bounds of the virtual curve, we can look at where those price bounds would have existed should we have decided not to amplify the curve in the first place, which means that we can compare things like relative trade volumes across that same price interval. And then after that, we deduced that the real curve, obviously it shares its midpoint, so its x0 and y0 coordinates have not moved, right? We've essentially stretched it in place. So both its marginal rate at the midpoint is the same as the reference point that we started with. And in fact, these 2 curves share exactly that x0, y0 coordinate. But the transformation that we've done, first by amplifying and then applying the horizontal and vertical shift parameters, have created these new, this new blue curve. And the points where it strikes the x and y axis are now algebraically defined as these 2 blue equations here. Okay, we're getting very, very close to the end, which is thankful. Be reminded that we now have 3 curves that all share a marginal rate expression that can be depicted as a tangent line at some point to that curve. And so here you can see that this orange tangent line, the gray tangent line, and the blue tangent line are all parallel, right? And that's not a mistake. And that's because they are showing you that at the point that it touches that curve, that is where the marginal rate is equal to some value. In this case, I've shown just the p high. We also know that P0, which is the initial marginal rate for whatever token balances you created with the reference curve, it's also going to be equal at these points. And here, the gray and blue lines are right over the top of each other because at that coordinate, they have exactly the same marginal rate. And then the same for P low. We've got tangent lines at the orange, gray, and blue curves, and they're not quite at the same points, but they, they're still depicting the same thing as we did for P high. Okay. The last thing that I really want to hit home about on this lecture, to sort of round out the discussion here on how to construct this amplification, is that there are now relationships that we can deduce from the algebra that we've got just in front of us that start to point at sort of a very deep fundamental concept in the geometry of the objects that we're using, which is these rectangular hyperbolas. The first thing we're going to do is to multiply p high and p low together. Okay, so again, I'm just going to show you that transformation. All I've done is literally taking the object that is p low and multiplying it by the object that is p high. Okay, and you'll note that the reciprocals here will cancel each other out, and we end up with just p high times p low equal to y0 over x0 squared, right, multiplied by itself, which means that the square root of p high times p low is equal to y0 over x0. That's interesting, right? That's useful. There are things that you can do with that because that is also equal to p0. And finding these kinds of algebraic identities that allow you to translate between different variables is something you need to get very good at doing. And this is going to be something that I examine heavily in the exam material at the end of this course. So definitely you want to start practicing this. Okay, what next? Well, let's have a look at the coordinates that we defined at the x and y axes for the real curve. If we take the ratio of those two things, note that the 2a minus 1 and a minus 1 components cancel, and you're just left with y0 over x0. Like, this appears to be a very, very important constant in all of the algebra and geometry that we're looking at. Let's put that back for a second. We can also do it for, make sure I get this right. Yeah, okay. So looking now just at the blue curve, we have a special name for those points on the x and y axis, right? And we call this the y-intercept and the x-intercept. And you will see me refer to that, a little subscript int. That's not an integer, that's intercept in the coursework material and in all of the lectures from this point out. So what we've defined now is this relationship. P0, which is the marginal rate at the starting token balance, whatever they were, is equal to y0 over x0, of course it is, but it's also equal to the square root of the two price bounds multiplied together, which is the same thing as saying that it's equal to the geometric mean or the geometric average of the two price bounds. And that's also equal to the y-intercept divided by the x-intercept. That's super powerful, right? This has a lot of geometric information in it. And just by taking these relationships and rearranging them, you can come up with an unlimited number of different geometric and algebraic identities for things that you might want to implement. And this means that there's an unlimited number of invariant functions that you can develop just substituting these things around. And so this is the homework that I have for you, is to perform some of these steps. I want you to show that this thing that I've already shown you how to do, right? The steps that I've done, there's nothing to show here in white. But I want you to do the green step. Show me that x0 times p high minus y0 over y0 over p low minus x0 is equal to all of these other things, right? And that's going to take you some time, right? There are short ways to do this, and there are long ways to do it. And when you're doing it, I want you to think, like, if you manage to get to the answer very quickly, I want you to stop for a second and think, I wonder how else I could have done it, right? Like, there's obviously a reason why I'm asking you to do this. And it's because I want you to get into the habit of rearranging these things algebraically and not using numbers anywhere in the process, right? The numbers stuff is stuff that we can save for plotting and graphing and that kind of thing. But the thing that I want to stress is that just because you finished the task doesn't necessarily mean that you should finish studying it, right? There might be more than one answer, and some of them might be more intellectually nourishing than others. And then homework assignment number 2 is to basically repeat homework assignment number 1, but now for 3 different invariant functions. So I want you to, so if you already completed last week's homework assignment, you don't have to do the x times y equals x0 times y0 because you've already done it. But now I want you to do it for the virtual curve and for the real amplified curve. And same as before, label all the axes, annotate everything, perform a swap. And when you're performing the swap, I want you to perform the same swap on all 3 curves, because I want you to see how some of these things interact with each other. And if you decide to study further, sure, you can do other things, like maybe try performing a swap between the same marginal prices over the same price interval, so on and so forth. But to qualify for the proof of knowledge, this is all that I'm asking you to do. So if you want to stop there and call it a day, that's totally fine. But you can see where this is going, right? Next week, we're going to be building on this again, and then again and again. And so the longer you go without completing these tasks, I think the more difficult it's going to be to keep up with the discussion. But that is the conclusion of today's lecture. I hope that you found it useful. Again, if you are frightened or overwhelmed, don't be. I promise that this stuff can look frightening, but it's really easy. Or it's not easy, but it's learnable. And I am making myself available to all of you. And so if there's something that you feel like requires a little bit more attention, or if you're uncertain of something, just reach out, right? It's not a big deal. You can contact me at any of these locations. Obviously, I'm active on the Discord now as well. Long term, that won't be true, but for while I'm doing this thing with token engineering, I am on Discord all the time. So yeah, thank you. I hope that you found this informative. I'm sorry we went 5 minutes over time.
Maya still has a question.
Maya, go ahead.
Hi, thank you so much. One quick question. So for the first part of the homework, where we're meant to derive the formula, right? Is there any platform that's really good for just writing that out in an easy way?
Oh, and you mean like so you don't have to do it with pen and paper?
Exactly, yeah.
Yeah, okay. So there's a couple. So the short answer is there are no there's no good ones that at least that I'm aware of. But you've seen, I think, from the office hours that you can use Word, right?
Yeah.
So if you hit Alt equals on Word, it gives you access to these things. So you can do it by mouse, but it also understands, like keyboard shortcuts. So if you write like A/B, for example, and hit the space bar, it will give you a fraction. And, it's got a bunch of other things up here, like, square roots and so on and so forth. You can do whatever you want here. So there's this. The other option is to use something like LaTeX, which is slightly worse. Let me show you how that works. So yeah, it depends. Like you might need an IDE or something, but how LaTeX works is it's like an actual programming language. So you need to sort of learn how things work. So like the square root of 3 is like this. If you want to do like a fraction, it's frac brackets, A over B, so on and so forth. So you can do this stuff in Markdown, but I think LaTeX is a horrible language. The output that it generates is quite beautiful, but the language itself is extremely verbose, right? Like it takes so long to write an equation. For reference, you can see like some of these things that I've written here for the for the lecture material is like it's a lot of code to get these equations written. So LaTeX, I would say like in terms of like looking at it, it's really, really nice. But in terms of writing it and studying, it's really, really awful. Like it's so much better to actually already know what you're trying to write when you come up to LaTeX. Whereas with Word, I can do stuff, I do stuff like this all the time, where if I've got, and just as an example, something like, A over B equals C, I can say, well, okay, then that means like A is equal to, B times the square root of C. Like this is actually a lot faster. And, I'm sure there are people that would say, oh, all of this clicking and mouse stuff is so inefficient, but I still think that, it's faster me doing this inefficiency than trying to, do it all in LaTeX. And I can also see things, coming out, as I compute them. So yeah, I recommend, Word for like scratchpad stuff. And when you're actually writing up your answer using something like LaTeX. But, for the purpose of this course, like it'd be super ambitious to expect that you would learn LaTeX. So I would recommend just using Word. If you don't have a Microsoft subscription, talk to me after the lecture and we can start thinking of like maybe we can explore some options together we can share with the rest of the group.
Thank you so much.
My pleasure.
And there was a final question again on where can I find this animation library?
Oh, yeah. Okay. So I will be uploading it. I'll be uploading it today. So I did create a GitHub. So this is the one for for the course. So I've got the the concentrated liquidity thing. This is the compiling like tech library. So remember that PDF that I created for you guys was written in LaTeX. So these are those equations that I was showing you in Markdown just a second ago. And then this is the the PDF that it outputs. This is the function of, I was using PDF LaTeX. And so that's that. I will be putting more things in here. So you can see that I've got the TE Academy Live Track 3 lecture stuff. And I've also got a homework, notes, and feedback. And this actually includes, some of the stuff that other people have submitted. And I hope that no one's embarrassed by this, because I will be sharing the things that you create with the other members in your cohort. And so, for example, we can have a look at, Tiago's code, which is, I think he's done a phenomenal job. And so there's no reason that I would imagine that he would be embarrassing us presenting this. But yeah, like here is, how he did it. And I actually really liked the way that he produced these. And it actually inspired me to make this animation at all. So thank you, Tiago. It's, it was really great to get that submission from you, because it made me think about something that I hadn't done before and that I wanted to do. So I will be uploading it to here. But if you want to see it quickly, I can show it to you. I'll be uploading 2 forms. I'll be uploading both the .py file, and I'll also be uploading the Python notebook. Okay, so let me just quickly walk you through how this works. So there is, a bunch of imports at the front, as there always is, and then there's like one major class, right, which I just call homework 1. And it's got, you can see it's got a bunch of attributes and a bunch of methods. So what it basically does is it takes in the things like the token pair, the swaps that you want to perform, and so on. And then it populates itself with like all of the data that it would require to draw any frame of the animation. And so when we run this, it will perform an enormous number of calculations, or it doesn't take very long. And then it will output a log file like this. And you can see this is, this is where I generated those first things from. And this is, hundreds of thousands of lines of code. So this is like many, 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 minor swaps being performed back to back. Oops, is that right? I missed, I'll reopen that. Okay, so that's the class, and you can explore these things if you like, it's got all of there's nothing in here that I don't mind people reusing or whatever. And then at the end, I've got 2 basically helper functions that just organize that class for you. So one is create trade animation. And this one, you need to decide like how many mini trades you do on the way to like the major trade. So this will basically take that DX and like divide it into 50 small amounts. And it uses a sigmoidal distribution so that you get the sort of slow start, slow finish on the animation. Otherwise, it's really jerky and it's very unpleasant to look at. You also have to give it the animation, name. If you don't, it will just save it as trade animation.mp4. And yeah, and you call it like this. Right, so here's just an example. So starting X0, Y0 balances, the names of the tokens, the trades that you want to do, the trade increments. I did 80 for the ones that I showed you guys. You can also do like many more trades than that. I think this is the actual, this is the actual animation that I created for the presentation today. So you can see it's got like many, many. And yeah, that's how you call it. The other function, which is the static figure maker, this one is so that, you don't always want an animation, right? So for like the one that I put in the Discord, I just want like a high quality like PNG. And so the static trade plot takes similar similar inputs, but also takes an index, right? So you can give it all of these, it will create the instance, and then you can generate as many figures as there are here by calling the index number. So this would be index 0, index 1, index 2, and so forth. And it will create those images and then just save it, you know, to the directory wherever you're running it from. So yeah, I will upload it to that GitHub page today. I will notify everyone in the Discord when it's ready. But yeah, you can do whatever you want with it. Have fun with it. If you're making the animation, just know that you do need to install FFmpeg codec on your PC, which is I don't want to say it's unusual because there is no installer for it, right? If you're on a Windows machine, you just basically just download the executable directly from the source, and then make sure that your system, that your environment variables include system path there. And if you're on Unix or Mac, I think it's slightly easier. I don't use Mac, so I can't tell you what the process is like, but I do know that it's easier to do on a Mac. But you do need the FFmpeg codec, otherwise matplotlib will have no idea what you're trying to do. But yes, it will be there, and I'll be happy for you guys to play around with it. Good.
Awesome, sounds good. Thank you so much for today. I think you guys should head over to the homework immediately. And we'll meet again next week, same time, same place. We'll drop the notes and the links to the slides and GitHub repos homework in the Notion. You'll find it there. Yeah, and see you on Discord, everyone.
Thank you,
Well, thank you very
everyone.
much,
I'll see you on
Mark.
Discord. You're welcome.
Bye.
Thanks so much.
Bye.
Bye.